Hello, welcome to this lecture series on electronic properties of materials. This is lecture number 12. In this lecture, I am going to discuss a new model for the electrical conductivity or thermal conductivity of metals. Okay, the model is actually quantum free electron theory. In the last few lectures, that is the last 11 lectures, we had seen the classical free electron theory of metals. Now I am going to start quantum free electron theory of metals. It is proposed by Sommerfeld. So this theory is also called as Sommerfeld theory of free electrons in metals. Okay, let's get started. First I'll give you some of the assumptions of this model. Okay, Arnold Sommerfeld actually developed this model using the quantum mechanical ideas, right? He also agreed that the conduction in metals, right, electrical conduction or thermal conduction, the conduction in metals are due to the presence of free electrons. Okay, so he accepted the Drude point, right? What is that? Free electrons, also called conduction electrons, are responsible for conductivity of material. Okay, it may be electrical conductivity or thermal conductivity, whatever it is. Okay, the free electrons are responsible. See here, that's why this model is called a free electron model, right? The electron is not attracted by the positive ions present in the crystal lattice. Okay, there is no attraction. So if I say it's a free electron model, it means electron repulsion, electron positive ion attractions are neglected here. Okay, so that means electron ion interaction. Ion means the ions present in the lattice point. Electron ion interaction and electron interaction are neglected here. They are neglected. Okay, so important point, keep this in mind. Next, so electrons are free, the free electrons are responsible for the conductivity. That's why this model is also called as free electron model. But Sommerfeld applied quantum mechanics for these electrons. So this theory is actually called as quantum free electron theory of metals. Clear? Now, free electrons, the next point, free electrons are quantum particles. They are not classical particles. Free electrons are quantum particles, not classical particles. You know very well, in Drude model, Drude assumed that the free electrons behave like classical particles. But according to Sommerfeld, the free electrons are not classical particles, they are quantum particles. Why? Because they have spin. Electrons have spin, and you know very well, spin quantum number for electron is half. Okay, if spin quantum number is half, if any particle has a half integer spin, we call those particles fermions. Okay, so the free electrons in metals are actually fermions, right? So Sommerfeld proposed this model by making use of the fermion theory, which we are going to discuss as we go along. Okay, to explain the electrical conductivity and thermal conductivity of metals, right? So keep this point in mind. According to Drude model, the electrons are classical particles. So if you assume electrons as classical particle, then Drude model can be applied. But now Sommerfeld utilized the Sommerfeld see these particles as quantum particles, right? So if you take the free electrons as quantum particles, yes, they are quantum particles. Why? They have spin. Okay, and since they have half integer spin, these particles are called fermions. For quantum particle, we are going to use Sommerfeld model. So remember, classical particle, Drude model, and for quantum particle, we are going to use Sommerfeld model. Clear? Then the next point. Next point, these free electrons, also called the fermions, okay, because they have half integer spin, so we can call them as fermions. These free electrons are they are all identical, okay, all are electrons, so identical. They are non-interacting. It was assumed that the particles are non-interacting. That means between one electron and another electron there is no repulsion exist. Okay, the particles are completely non-interacting, and the particles are indistinguishable particles. You cannot distinguish one particle from the other particle. You know very well, if you assume the particles as classical particle, then we'll use Maxwell-Boltzmann statistics. In Maxwell-Boltzmann statistics, we usually assume particle as distinguishable particle. Clear? But you know very well, the free electrons in metal behave like a gas, right? So they move randomly here and there. So it is very difficult, or it's not possible to distinguish one free electron from the other free electron. Therefore, the free electrons in metals are definitely indistinguishable particles. So this assumption is very, very valid. Okay. If the particles are indistinguishable, okay, they are identical, non-interacting, and they have half integer spin. Spin is half. They are fermions. So to treat fermions, we should not use Maxwell-Boltzmann distribution, Maxwell-Boltzmann statistics. We are actually use quantum statistics. For fermions, the quantum statistics that is available is Fermi-Dirac statistics. So what we are going to do in this model is that we are going to use Fermi-Dirac statistics instead of Maxwell-Boltzmann statistics. Why? Because the free electrons are not classical particle, they are all quantum particles. Clear? Then, in Drude model, free electrons are assumed to obey Maxwell-Boltzmann statistics, because they are in Drude model it was assumed that the free electrons behave like classical particles. Okay, but here we are going to use Fermi-Dirac statistics. Right? Keep this point in mind. Then the next important point is that since free electrons are quantum particles, they are fermions. So you know very well, fermions and bosons must obey Pauli exclusion principle, a Pauli principle in general, right? So free electrons obey Pauli's exclusion principle. What does this principle says? Suppose if you have an energy state or energy level, in this energy level you can place two electrons with opposite spin. See, this is not a spin state, this is an energy level. In each level you can place two electrons, or in each state it is say it is a spatial state. Okay, in each spatial state you can place two electrons with opposite spin. Clear? This is what we call as Pauli's exclusion principle. You cannot put more than that, right? So free electrons obey Pauli's exclusion principle, right? Then according to which two electrons with the opposite spin, two electrons with opposite spin can be placed in an energy state. Remember, this is not a spin state. If it is a spin state, you can place only one electron, but it is not a spin state, it is a spatial state. Okay, then the next point, inside the metal, listen, we are assuming that there is no interaction between electron and there is no interaction between electron and the positive ions present in the lattice. Okay, so all interactions are completely neglected. Therefore, inside the metal, potential energy is assumed to be constant. Okay, so it was assumed that the electrons travel right inside the metal with a constant potential energy. Right, since the potential energy is constant, you can also assume it as 0 for convenience. Okay, so for convenience you can also assume it as 0. So free electrons are moving right inside the metal with a 0 potential energy, right? So the potential energy experienced by the free electron is 0. But these free electrons, they cannot jump out of the metal. Why? Because on the wall and outside the wall, the potential energy is assumed to be infinite. So potential energy is assumed to be infinite on the wall and outside the wall. Therefore, the free electrons cannot jump out. Clear? So this is another important point. Keep this in mind. Then last point I like to give here, free electrons. Okay, the free electron can have only certain allowed energies. Okay, they cannot take just like that any energy, right? Because we are going to use quantum mechanics for the free electrons, right? So for the electron, only certain energies are allowed. Okay, so electrons, these electrons, the free electrons can present only in certain allowed energy states. Okay, so the energies of the free electron are quantized. Okay, so energy is quantized. This is another important point to keep in mind. Okay, so these are all few assumptions of Sommerfeld model or quantum free electron theory of metals. With these assumptions, okay, I am going to show you some of the important expressions, right, which we'll discuss as we go along, right? Then now let us consider a free electron moving in a cubical piece of metal. Okay, I'll take a cubical piece of metal, right? Cubical piece of metal. Okay, let us take this corner as origin. You take this as x-axis, this as y, and this as z-axis. So the electron is moving freely inside the metal. Let the volume of this metal piece be V. So V is the volume of the metal piece. Okay, so let us consider a free electron moving in a cubical piece of metal of volume V. Okay, then, and you know very well, inside the metal potential energy is constant, or we can assume it as 0 for our convenience. I told you this point already. And on the wall, outside the wall, potential energy is infinite. Okay, then now I am going to write the Schrodinger equation. The Schrodinger equation for the free electron. Okay, you take any one free electron first. The Schrodinger equation for an electron can be given as minus h bar square by 2m plus del square psi, this is kinetic energy part, plus potential energy into psi equal to E psi. This is the general form of Schrodinger equation. And here potential energy is 0. Potential energy is 0. Therefore, this equation get modified as, let me write the next page. So this equation get modified as minus h bar square by 2m into del square psi equal to E into psi. Let me put this energy as E. Okay. Now this is Schrodinger equation in 3 dimension. What is the general solution for this? See, in quantum mechanics we have discussed particle in 1D box model, 2D box, 3D box, okay, rigid rotor, etc., etc. So we know very well what is the general solution for this equation. Okay, so I'll give the general solution directly. The general solution for this is psi, which depends on k, and it is a function of the position vector r. Okay, psi k of r equal to normalization constant a into e power iota I k dot r. Okay, this is the general solution for the for this Schrodinger equation. Okay, for an electron moving in a metal of volume V. Clear? Now, what is k here and r here? K vector is nothing but x component of k into I vector plus y component of k into j vector plus z component of k into k vector. Similarly, r is the position vector, which is nothing but x into I vector plus y into j plus z into k. right? So if I take k dot r, I can write the general solution as psi k of r. What is this k? We'll discuss. Psi k of r equal to normalization constant a into e to the power I into, so if I take a dot product of k and r, I'll get kx into x, okay, kx into x plus ky into y plus kz into z, right? So this is the general solution, right, for the electron moving in a cubicle in a metal, right? Up to now I did not impose any boundary conditions here. This is the general solution, okay, general solution for a particle moving in a constant potential, right, in third dimension. Clear? Now what I'm going to do, I'm going to apply the boundary conditions, right? So first of all I'll normalize this constant, okay. So normalization of psi, let me do it in the next page, okay, normalization of psi. How to normalize psi? You know very well, the electron cannot jump out of the metal, therefore the electron is completely confined within the metal, okay. So integral psi k star into psi k into d tau is equal to 1. This is the normalization condition, you know very well, okay. What is the expression for psi k? Psi k is equal to a into e power I iota k dot r. And what is psi star? Psi star means instead of I you put minus I, that's all, okay, and write the expression as such. A into a is a square. As we are interested only on magnitude, okay, I am not putting any star over here, okay, I am not putting any a star here, okay, we are interested only on magnitude of the normalization constant. So a into a is a square, and e power minus ik dot r, e power plus ik dot r, if I multiply I'll get e power 0. E power 0 is 1, so just leave it. So 1 into d tau is d tau, okay, integral d tau equal to 1. Here I am integrating all over space, all space, integrating over all space, right? So since you are integrating over all space, right, if I integrate through all space, I'll get what is I'll get what is called the volume. D tau is the volume element, small volume element. If I integrate through all space, okay, I'll get the volume of the metal, right? So a square into v equal to 1, or a square equal to 1 by v, okay, or a is equal to 1 by square root of v. This is the normalization constant for the free electron which is confined in the metallic piece, okay. So the normalized wave function is psi k of r equal to 1 by square root of v into e power I into iota k dot r. So this is the normalized wave function for a free electron moving in a cubical metallic piece of volume v. Clear? Listen, up to now, up to this I didn't apply any boundary conditions. Now I'm going to apply boundary condition for this, right, and I'm going to give you the proper wave function, right, for the free electrons, okay. Now what's the boundary condition we are supposed to apply here is that now I'm going to apply I'm going to apply the boundary condition called Born-Karman boundary condition. Listen, this boundary condition is applicable, we have to apply this if the particle carry energy and charge. You know very well the free electrons which are present, right, the free electrons which are present in the metal, they not only carry energy, they also carry charge. Therefore we cannot use standing waves, we cannot create or we cannot construct standing waves for electrons here. We have to create traveling waves, okay. So for traveling waves the boundary condition is, the boundary condition that we are supposed to use is this. This is the boundary condition we have to use for the traveling waves. Clear? So the condition is Born-Karman boundary condition, according to which the wave function at x, y at the point x, y, z should be exactly equal for the wave function at x plus L, comma y, comma z. What is L? L is the length of the metal along x-axis. Okay, length of the metal piece along x-axis. So you take any point right inside the metal and you travel a distance L right along the x-axis, you will once again reach the same point. Okay, it is called cyclic boundary condition, something like cyclic boundary condition. So this is valid along x-axis, this is valid along y-axis, this is also valid along z-axis. Okay, so this is what we call as Born-Karman boundary condition, and this condition should be applied for traveling waves. Clear? Now what I'm going to do, I'll take the first condition here. So let us apply the boundary condition, the first boundary condition. What is the first boundary condition? Psi of x comma y comma z is equal to psi of x plus L comma y comma z. Clear? And you know very well the general formula for the wave function is 1 by square root of v into e power iota k dot r. If I multiply the k vector and r vector, if I take dot product, I'll get this. Clear? Similarly, in the left hand side, the wave function psi x plus L comma y comma z can be written as 1 by square root of v e power iota. Here k dot r we should put, but here the r is not just x, it is just x plus L. Clear? So r is x plus L I vector. Here r is right in this case. In this case r vector is nothing but x plus L I vector plus y j vector plus z k vector. So we have to use this r vector, okay, to get this wave function. So if I multiply k dot r, I will get this expression, kx into x plus L plus ky into y plus kz into z. Now cancel 1 by square root of v in both sides. So and you can also separate this as e power I kx into x plus L into e power I ky into y into e power I kz into z. You can separate this. Similarly, you can separate this, and you can also separate e power I. See, let me just write and show you here. So what I'm trying to say is, you can separate this actually. 1 by square root of v, 1 by square root of v cancel. So you can separate this as e power I kx into x into e power I kx into L. You can separate this. You can also separate this e power I ky into y e power I k z into z. Right? In the right hand side we have e power I kx into x into e power I ky into y into e power I kz into z. You can separate like this. Now this and this cancel, this and this cancel, and this quantity cancel. So we have only e power I kxl in the left hand side, and in the right hand side we have 1. Clear? So what we get here is, if we cancel the terms, I'll get e power I kx into L equal to 1. Right? If you apply Euler's theorem, you'll get cos. So this is, you take this as theta. E power I theta can be written as e power I theta equal to cos theta plus I into sin theta. Right? So similarly, I am writing here as cos kx into L plus I sin kx into L equal to 1. This is valid only if kx into L is some integer multiple of 2 pi. Why I am saying this? Suppose this integer can be nx equal to 0 plus or minus 1 plus or minus 2 etc etc. First I will put nx equal to 0 here. If I put nx as 0, this entire term becomes 0. That means kx into L is 0. If kx into L is 0, I'll get cos 0 here and sin 0 here. You know very well sin 0 is 0, whereas cos 0 is 1. So you'll get 1. If I put nx equal to plus 1, so if I put 1 here, 1 into 2 pi is 2 pi. So kx into L equal to 2 pi. If I put 2 pi here, I'll get cos 2 pi plus I sin 2 pi. You know very well, sin all pi values are 0. So this becomes 0 and cos 2 pi is plus 1. You will get, so this equation is satisfied, okay, even if I put nx equal to plus 1. Okay, and if you put nx equal to minus 1, since cos is an even function, okay, cos of minus 2 pi is also equal to 1. Therefore this nx, okay, takes only certain allowed values, so it is called a quantum number. Okay, what are the allowed values of nx? 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Clear? If I rearrange this expression, I'll get kx equal to 2 pi nx by L. This is the value of kx, right? Depending upon the value of nx, kx takes different value. Clear? So what are the values of kx? If I put nx equal to 0 here, I'll get kx equal to 0. If I put nx equal to plus 1 here, I'll get 2 pi by L. If I put nx equal to minus 1, I'll get minus 2 pi by L. So the allowed values of k are 0, plus or minus 2 pi by L, plus or minus, if I put n equal to 2 here, okay, 2 into 2, 4, plus or minus 4 pi by L, like that it goes. Okay, these are all the allowed values of k. That means k cannot take just like that any number. K takes only certain allowed numbers. Are you able to understand? Therefore the energy, right, is not continuous. Energy, right, or there is a discontinuity from one state to the other state. Okay, so so in a similar manner, if I apply the same boundary condition for this and this, right, I can write ky equal to 2 pi ny by L, and I can also write kz equal to 2 pi nz by L, and the allowed values of ny and nz are given here, right? Depending upon the value of nx, ny, nz, you will get the energy. Why? You know very well the energy formula, right? The energy expression here is equal to, if you do a derivation, right, we'll get E is equal to h bar square by 2m into k square. Okay, what is k here? K is nothing but this is a net k value. Actually the net k is made up of 3 components, so kx square plus ky square plus kz square. The sum will give you k square, and this is the expression for energy. Clear? So depending upon the value of nx, ny, nz, you will get a specific value of kx, ky and kz. By applying kx, ky, kz value, you can calculate energy. Is this clear? Right? So so here the electrons present in certain allowed states, and for the allowed state we have a specific energy. Okay, so it is very clear that electrons inside the metal, okay, assume that the electrons freely moving inside the metal, right? If you apply the boundary condition, then the electrons can take only certain allowed energies. So energy of the electron is quantized. Clear? Then if I rearrange this expression, okay, kx square plus ky square kz square, right, bring this 2m and h bar square to this side, you will get this. This is an equation of a sphere, right? Because for a given energy, this has become constant. 2m is mass of electron, h bar square, everything is constant, right? So kx square plus ky square plus kz square is a constant, and that is nothing but the equation of a sphere. Clear? So similar to equation of a sphere for a given energy E. So this equation appear like a equation of a sphere, right? Now okay, I stop here. We'll continue this in the next class. Okay, I just stop here. Thank you for listening.